Hi, and welcome to this calculus video. In this video, I'm going to attempt to establish the connection between Riemann sums and the definite integral. So the first thing we want to kind of consider is when we see a definite integral, we usually see something like this. This integral evaluates the function's value from A to B, and when we do this, we consider the signed areas. So essentially, we need to figure out where this formula came from and how we figure out the value of the integral by using the signed areas under the curve. So in order to do this, we're going to use Riemann sums, which you should know from previous lessons are our rectangular approximation methods. And those rectangular approximations include LRAM, MRAM, RRAM, and then there's the trapezoidal approximation method, which is not a Riemann sum. So Riemann sums are only rectangles. Okay, so let's think about how we're going to use these strategies to approximate the signed area under a curve. So here's the curve that I've drawn. So we're going to evaluate the integral from a to b of f of x dx, which means we're going to start at a, we're going to go to b, and we want to consider the signed area trapped between the curve and the x-axis. So the area over here we would consider to be negative, and the area on this side would be positive because it's above the x-axis. Alright, so the first thing we want to do is decide how many rectangles we want to break this into, because remember we're using our rectangular approximation, and let's let our number of rectangles be n. So we need to figure out how wide each rectangle is, and we're going to call that width, uniform width, we're going to call that a delta x, or our change in x. And in order to figure out how wide each rectangle is, we need to take the length of our interval, which is b minus a, and then divide it by the number of rectangles we want, which is n. So this is the first thing we're going to do. So I'm going to go ahead and start doing that and then tell you how we are going to proceed with areas. Okay, at this point I've labeled some of the intervals on my x-axis, and you can see my starting point here is going to be x naught, x sub 1, x sub 2, x sub 3, and so forth. In fact, I kind of skipped a bunch here, so we're going to call this one here x sub k, which means this is x sub k minus 1, and then as I get closer to the end, this is the end of my nth rectangle, so that's x sub n, and this is x sub n minus 1, and x sub n minus 2, and so forth. So our first delta x would be right here, and the way we compute that delta x sub 1, we'll call that the width of our first rectangle, is our x sub 1 minus our x naught. The way we would figure out the second width here, we would call that delta x sub 2, and that's going to be x sub 2 minus x sub 1. Now remember, these are all of uniform width, so we don't have to worry too much about labeling all of these. Now, if I go ahead and draw my rectangles, I'm going to draw vertical lines down to my curve, but then I need to decide where I'm taking the height from, or the length of the curve. If the width is delta x, I need the height to be my f of x. So I need to decide where that x is going to be. Well, we could do the left side, that would be an LRAM, or we could do the right side, that would be an RRAM, or we could do the middle, that would be an MRAM. I can also pick an arbitrary point anywhere between x naught and x sub 1, and so that's what I'm going to do. I'm just going to pick something over here. I'm going to call that c sub 1. So that would be my first input value. So if I want to drop that vertical down and then draw my rectangle, and I'm going to highlight that for us, what we have now is my first rectangle. So let's go ahead and write an expression for that particular rectangle. The expression for that would be, let's just call it a sub 1, and then our a sub 1 is going to be our delta x sub 1, our first width, times the function evaluated at that x value we picked that was between x naught and x sub 1, which was c sub 1. So this is our first area. All right, let's do that again for the next one. So we're going to grab another random x value between x sub 1 and x sub 2, and we are going to call that c sub 2. So if I grab c sub 2, I'm going to put that right there, and I'm going to draw that all the way down to my function. I'm going to make my rectangle. So notice these rectangles we're making, they're not LRAM, they're not RRAM, they're not MRAM, they're kind of random RAM. So let's call these random RAMs. I've highlighted that area as well, so now we are going to write an expression for that. Okay, there's my second area expression. We're just going to continue doing this all the way down the line. So I'm going to write a few more and then we're going to discuss what I've done. Okay, I've got my third rectangle. My area of my third rectangle would be delta x sub 3 times f of c sub 3. And then I realized, okay, I'm going to have a bunch of rectangles here, but we're not sure how many because we're not sure what n is. But eventually, I'm going to get to my kth area. So my kth area would be represented by this rectangle. And again, we need to pick a c value in between x sub k minus 1 and x sub k. And since we're using our random RAMs, I'm going to use this. I'm going to call it c sub k. And I don't know exactly where it is, but it's somewhere in that interval. So it's going to get us a rectangle that would be appropriate. So at this point, hopefully you're seeing a pattern merge. I'm almost done here. I'm going to have a bunch of rectangles in between my kth rectangle and my nth rectangle. So let's kind of finish this up and then maybe we can consolidate all of these terms because I sure am adding a whole lot of things together. So we're probably going to want to use a better way to write that. Okay, so at this point I have an expression written that represents the infinite number of rectangles you would need to find the signed area between the curve and the x-axis, which would be the value of this definite integral right here. So now our task is to consolidate this into something a little bit more manageable. At this point we're going to start using a lot of algebra, so I'm going to scroll up, but we're going to think of this as a sum, and that's important. So let's kind of do a little bit of hocus pocus here. Now we talked about all of these delta x's being exactly the same width, so let's just call those generically a delta x, and we're going to factor them out of each term. When we do that, we get something that looks like this. Now, when we add a number of terms together, we can use summation notation. So instead of writing the word sum right here, what I'm going to do is I'm going to use summation notation. So our sum, which remember this is going to be the value of the integral, is going to equal, using our summation notation, our k's are going to start at 1. And the reason I'm using k is because that is the variable that we used for that generic rectangle that was in the middle of our diagram. Our k's are going to start at 1 and they're going to go all the way to n, and what we're adding together is delta x times f of c sub k. So this generic term right here is really important for helping us establish a formula where we can substitute the k's starting at 1 and going all the way to n. So at this point, we have just created something that we can turn into an integral. Now, this isn't quite the value of the integral yet. I was a little bit premature in writing that, but we're going to get there. So this sum only equals the value of the integral if one of two things happen. If the number of rectangles we have goes to infinity, that means our delta x's would go to 0. In other words, the change in x would become so infinitely small that we would have an infinite number of rectangles. So the way we can represent that is to use a limit. So we are going to put that in front here. The limit as delta x goes to 0 of the summation would give us an infinite number of rectangles. Another way we could write that, instead of the limit as delta x goes to 0, we could do the limit as n goes to infinity. So if our n up here goes to infinity, that's going to produce the same result. So another way this could be written, exactly the same, but we're going to replace the limit with delta x going to 0 with n going to infinity. So both of these Riemann sums, including the piece right here that is the limit, give us the actual value of the signed area trapped between the curve and the x-axis. So let's think back to our integral. Remember, our integral was the integral from a to b of f of x dx. Now, if you look at the different parts of our summation, the f of c sub k turns into our f of x. The delta x turns into our dx, because that means change in x. And then the a and the b, remember, our delta x was equal to our b minus a all over n. So the a and the b are kind of hidden. You don't always see those in the summation notation, but they are there at the beginning when we calculate this delta x. So essentially what we've done is translated our Riemann sum into an integral sign. Now remember, Riemann sums are always, always, always rectangles. So if we go back to this Riemann sum we have, and we consider the Riemann sum is the area of a rectangle, the delta x is the width, and the value of the function at any given input is our height. Trapezoidals are not Riemann sums. They do a great job at finding the area under a curve, but remember, if you're using Riemann sums and you want to use the summation notation so you can translate it into an integral, you have to use rectangles. All right, I hope this formula right here makes a lot more sense, and hopefully this graph gives you something to think about. I know it's a lot to digest, but it's a really, really nice thing to understand and to be able to explain. I hope you enjoyed this video.